This is lecture 2 for Calculus 3, and it is on vectors. You might have encountered vectors in trig, and in that case the vector was written as basically as a sum of some components. Instead, what we want to do is look at the most general definition and the most general form of the vector. And this most general form is coordinate free. In other words, we don't need any coordinate system to define the vector. We will define the vector as a directed line segment. And let's see what that means. Okay. It brings a visual idea to mind, but we can look at each piece of the definition here. So if we look only at the word line, it means that it's linear, it's straight, like an arrow. And so this means it's linear. So that's something about a vector, and it also, we get the physical image of the arrow, not just from the linear, but from something else as well. Using the term line segment means that its length is finite. In math, a line sorry, I'm trying to write well with this new tablet. Okay, so in math, a line itself goes from minus infinity to infinity. It does not have finite length, but a line segment has finite length. So you put these two together, it's something that's straight, linear, and it has finite length. Now the next piece of the definition says directed. It means it's going to point in a certain direction. That's all that a vector is, a directed line segment. Okay, so that gives it some attributes. One of them is that it is something with length, although we don't even know how to define length yet. We can assume we have an intuitive idea that something has a length. So it has a length, and it's finite. And the fact that it points in a direction means that it has an initial point and a terminal point. So the vector gets a length, a tail, and a tip, and is pointing in a direction. What it doesn't mean is that it is fixed in space. The vector is not located in space. If it is moved around in space, as long as it keeps its same length and its same direction, it maintains its identity, no matter where it is. Okay, this means that if I have a vector, and I'll draw it like an arrow here. Now if I move that arrow around, let's see if I can draw the same arrow again. And it's sitting over here, it's the same arrow. It's the same vector, because it has the same direction, more or less, and the same length, or it's intended to. I can even turn it around and I can put it anywhere I want, and it is still the same vector. That's sort of hard to figure out. We're so used to putting the vector on a coordinate system. In that case, it is fixed to the origin, and it's not considered a vector. It has a little bit of an adjective that goes with it, and if it's fixed to the origin of the coordinate system, it's called a position vector, or sometimes standard position vector. That vector is fixed. Its tail is sitting right on the origin. Okay, but ordinarily a vector is not fixed. So without this adjective of position associated with it, the vector can be moved around. Along with this definition, there are certain rules for adding vectors together and for multiplying them by scalars, and then we develop multiplication by other vectors. So what you can do with the vector is you can multiply it by a scalar. Oh, I didn't define what a scalar was. A scalar is not a vector. Okay, so if you want a GNU definition for a scalar, it's not a vector. A scalar is a number. It has a value, but it doesn't have a direction. In physics, you can think of a velocity vector or a force vector. They both have magnitude and they have direction. They have length and they have direction. A scalar would be like mass or temperature. It's only a number. As far as the addition, you can add and subtract vectors together. So a vector can be added to another vector, assuming those two vectors. But if we let alpha be our scalar, we cannot add a vector and a scalar together. You can add two vectors together. You can add two scalars together, but not the vector and the scalar. You can also subtract, but that has to do with scalar multiplication. Okay, so here are the ways you can multiply a vector. You can multiply it by a scalar, and that's called scalar multiplication. Scalar multiplication. That's one way to multiply vectors. Another is for two vectors to multiply together and produce a scalar. That's called a dot product. A dot product takes two vectors, let's say v and u, connects them with a dot, and ends up with a scalar. We're letting alpha be our scalar here. There's another type of multiplication, and that's you take two vectors, you apply what's called a cross product, and you get another vector. So that's your cross product. And so those are ways that you can multiply vectors together. There's u cross v, and that equals another vector w. Look at this dot and this cross. If you have just regular numbers like 4, you go 4, you put a dot here, 5, and that's the same as saying 4 times 5, and in that case they both equal 20. There's no difference between the dot and the cross when you're just working with scalars. But when you work with vectors, one of them becomes what's called a dot product, yielding a scalar. The other is the cross product, and that yields a vector. Now right now we've called vectors arrows, but when you get to linear algebra and beyond in mathematics, you find out there's a whole lot of other things that act like vectors. They behave like vectors. They have the same rules. You can multiply them by scalars. You can use a dot product with them or a cross product with them. You can add them in certain ways, and they have this length and direction associated with them, but they are not arrows. So for that reason, a lot of the things that we do here apply to more than just arrows in the plane. If you remember that first lecture with that list from Wikipedia that listed all the different fields from relativity to economics, all sorts of fields that use the tools of Calculus 3, a lot of the entities they're working with are vectors, or considered to have these attributes of vectors. So studying them has more general applicability than just the vectors that we're used to in physical space. So now we'll look at the rules for scalar multiplication of vectors. The idea is that you have this vector that's shown here as u, and you can multiply it by a scalar alpha. If alpha is greater than 0, then the only thing that changes is the length. And that's shown here. Here's the vector u. It's multiplied by the scalar 2, and now it's twice as long. Notice that it's offset in space, and that's perfectly fine, because vectors are not tied to a point, at least not how we're discussing them here. Okay, if alpha is less than 0, then the length changes by the absolute value of alpha, and the direction changes so that it now points in the opposite direction. So here's your vector u. right here, gets multiplied by a -1. It keeps its same length, but it's just going in the other direction. In this example, you could multiply it by, say, a -1/2, and it would go in this opposite direction. Whoops, what happened? It's going to go in this opposite direction, but it's only going to be half as long. So this would be, I have to get the other tool here, sorry. This would be -1/2 u. -1/2 being the scalar. And now we can take scalar multiplication and we can create the very useful unit vectors. And what's a unit vector? We talked about these a little bit before when we were talking about coordinate system. It's a vector that has a length of 1. Remember, a unit circle has a radius of 1, so a unit vector has a length of 1. And now let's define the length of a vector. We haven't gotten into too much notation here, but this is going to be the length of a vector. Sometimes it's just written with one line, and that's the vector there, and that also could be the length or magnitude of the vector. The important thing here is that you get the length of the vector by measuring it or somehow. Since we don't have a coordinate system, you're going to have to measure it. Okay? But note that length is just a number. It's a scalar. If something's 5 feet long, it's 5 feet long. 5 has no direction. It's only a scalar. On top of that, it's a positive scalar. If you remember from the previous slide, the rule is that if you multiply by a positive scalar, the only thing that changes is the length. So if you take a vector v and you divide it by, this is going to be a non-zero vector, you divide it by its length or magnitude, you will create a new vector. Denote that new vector with a hat, although that hat didn't fit the vector so well, as a unit vector. This is a unit vector. It means a vector of length 1 that points in the same direction as v. These are very handy, and we'll make a lot of use of them in the future. If you recall from the coordinate systems that we had basis vectors I, j, and k, and in the Cartesian system we had r and theta, and of course another one I guess we can call z. In the cylindrical system and in the spherical, there was I used rho, theta, and phi, and that was for the spherical system. All these basis vectors are unit vectors. They have a length of 1. You don't have to divide them by anything to get that length of 1. But those are unit vectors also. So now we're going to work through vector addition using this coordinate-free definition of a vector as a directed line segment. So we have two vectors here. Let's just kind of should have made this diagram a little bit better. Here's a vector A, and here's the vector B sitting over here, although it gets labeled by A plus B kind of round on top of it. Let me draw some more vectors here. It'll be better. So I've got, I don't know what happened there. Here's one vector, and now let's get another vector, blue one, and we'll call that, we're just going to call that B. So that's A and B. To add the vectors, remember vectors aren't tied in space, you take one of the vectors, so I'm just going to take the blue vector and I'm going to stick it on the end of A. So when I move the blue vector over, it has to keep its same direction. It just happened to get moved over. I don't know why I decided to put those extra arrowheads. There we go. Okay, so what I have now is I have the vector A here, and I have the vector B here. You can think of that as a copy of B, but it doesn't matter. It's still the same B. Now to add them, I then connect, probably should put that in a different color even. I connect the tail, the terminal end of A, with the tip of B. Okay, so that gives me, this green is A plus B. So that's how to add vectors without a coordinate system. That is a plus, and I don't seem to have an eraser other than to erase the whole board. Oh, maybe I could do that. Oh, I know what I can do. All right, here we go. So now I do have an eraser. I just have to paint it over in white. Okay, so we will now try to put a diagram back together to have it look a little bit nicer. This is A plus vector B. So now it's also a vector. So it's a directed line segment. You just as easily could have moved A over to the tip of B and stuck it up there. You then have to have need a red arrow now. I'm going to move where's red? Here it is. Okay, so I'm going to move A, so A would get stuck up here, and actually you can see it ends up being a parallelogram. This actually looks like a rectangle, but this one looks more like a parallelogram over here. But you end up with the same A plus B. And we do expect that. We expect A plus B to equal B plus A. We expect that addition is commutative. And it is here for vectors as well as for numbers. So that's the coordinate-free parallelogram rule for adding vectors. You put them tip to tail, and the resultant is A plus B. Now we're going to use that with our unit basis vectors to create the coordinates, the coordinate form, and the components for the vector. So let's remember our basis vector. So I is a unit vector. It has magnitude, it has direction. It is subject to scalar multiplication. And so I'm going to multiply it by some number that I'm going to call Vx. This is just a scalar. It's just a number. You may recall that the unit vectors, that the basis vectors are unit vectors, so they have a length of 1. So let's just kind of sketch one of those in. Okay, so if I say that this is a length of 1, I'll just put it here, you can kind of see it, then that's the I, although no one ever draws the I in. Instead, they just take the I and write it here at the end of the here, and just write the J up here. But I'm going to put that in. That's my unit vector. It's a unit vector pointing in what I'm calling the I direction. If I multiply it by Vx, it's going to get either longer or shorter, but it's going to continue to point in the same direction. In this case, Vx must have been 1, 2, 4. So here we go. Vxi is a vector in the direction of I that has a length of 4. Okay, I'm going to do the same thing with the J basis vector. I'm going to multiply it by a scalar, a number that I'll call Vy. So this is just another scalar. So it will be, obviously it's 2. So this would be a vector in the same direction as J, but of length 2. Actually, if you want to do it as a position vector, then it would have been over here, because here's J. Now I'm going to add them together using the parallelogram rule. In the parallelogram rule, I can move them because, of course, the vectors aren't tied to space. And so I'll put this vector here. Whoops, the wrong tool. Sorry. I'm getting used to this thing. Okay, I take this vector that I created here, it's right over here, and I move it so that it is tip to tail with the one in the I direction. Adding them together, I get the vector V. As I mentioned before, this V as it's sitting here, it's a position vector because it's sitting at the origin. But it really is, being that it's really a vector, it can be moved anywhere in space. So we really could move it. But the way it's sitting here, it's a position vector. And what is it now? This v is the sum of vx in the I direction plus vy in the j direction. And that's how often vectors are approached in trig. They are the vector sum of two vectors, one in the I direction, one in the j direction. And this is your coordinate definition or your coordinate expression of the vector. You can see with this you will have to work pretty hard to say that it could be moved in space. In fact, you're not going to get it from here. All you can get is this is a position vector. We didn't talk about the notation of vectors. Okay. If you have a computer system or something you've got access to, some kind of printing, then a vector is denoted by something in boldface, V. Okay, see that V? It's bold, then it's that denotes that it's a vector. The ones that are not bold are scalars, and that's one of the basic ways to distinguish vectors from scalars in printing. There's another way that you can take this V and you can superimpose over it an arrow. So you might write that. Let me write it for you here. So let's say I have W, and I want to show that that's a vector when I don't have access to bold, for example, when you're handwriting or trying to write on this tablet. Whoa. I don't know how I get those extra arrowheads. Probably operator error here. Let me try again. So here is U, and I'm trying to show it as a vector when I don't have boldface available on the end of my pen. I can put a line over it. Some people put, instead of that, they put a just a solid line. That's another way you can do it. You don't do all these at once. And the other is kind of a harpoon. So those are three ways to show that a quantity is a vector. And then, like I said, by contrast, the ones that are not in bold or don't have arrows, harpoons, or lines over them are considered to be scalars. But that doesn't need any coordinate system. Oh, I didn't mention also, but you've seen it already. If you have a vector v and it's a unit vector, that's a bad example, let's say u, it's a unit vector, and you put a hat over it, that denotes that it's a unit vector with length 1. Once you have the components, you have many more ways to write vectors. First, we do, of course, consider the vx and vy to be the components of the position vector. The components here, right? And if it's in 3 dimensions, then you will also have a vz term for another component. Now you can write them using the basis vectors. So it's vx, the length in the I direction, plus vyj, and if you have a z, you'll have vz in the k direction. Another way to denote the vector is to write the components in pointy brackets. That brings up an issue because some fields, such as linear algebra and some other areas of mathematics, likes to write vectors using just parentheses. For this class, I don't want you to do that. I want you to use either the basis vectors or the pointy brackets. So we're just going to cross this off. Okay. Because we're just trying to get everything sorted out first. And when you first start working with vectors and scalars, it's very easy to confuse them. And students do confuse them. They'll write something that should be a scalar as a vector and vice versa. And that, like I say, that has to be sorted out. So let's not add the idea of using these parentheses in to the mix. You can do that later. The parentheses will be reserved for points. So if you have a point, for example, in 3-space and Cartesian coordinate system, x, y, and z, okay, those are the coordinates of the point. There's another way you can write vectors, and that's you can write them in matrix notation. Here's a row vector, and here's a column vector. Once you have the components, it's particularly easy to add the vectors since you don't have to do any geometrical arrangement of them. So if we're trying to add v plus w, we write these in component form. Just say two-dimensional vector vx plus vy, and then we have a wx and wy for the w, two components. Now when you add them, you can only add i's together and you can only add j's together, just like it's in algebra. So this would be vx, add the x components together, and you'll note here that we still have a vector. And that's, of course, considerably easier than trying to move vectors around. However, using that coordinate-free approach is really the way to start. It is the most general way, so from that most general look at vectors, we're able to deduce all sorts of properties about the vectors and properties about their operations. Then the coordinate system comes later. We're here using this XYZ coordinate system, but as you know, for 3D anyway, there's two more coordinate systems. They aren't exactly that easy to use, the other coordinate systems here, especially for addition, because they move around with the point. So if both vectors are applied at the same point in cylindrical or the same point in spherical, then you can use the r theta and z or r theta phi components and add them together. Otherwise, you can't. So it's more common in those cases to come back to the XYZ coordinate system. But it is not the only coordinate system, and so it's actually better to use that sort of as an afterthought and develop all the properties like we've done and like we'll continue to do for the coordinate-free vector. Another thing that we can do with components is to quantify the angle. We say the vector points in a certain direction. Well, that says angle with respect to something. You know, angles are measured with respect to some other vector, some other direction. So for a two-dimensional vector, now we have the angle with respect to the y-axis. It's the arctangent of y over x. It's very familiar. We can also calculate the length of the vector as the square of vx squared plus vy squared, and this all extends to higher dimensions. At least the magnitude extends easily to higher dimensions. For the angle, we have to do something different. But at least now, using the components, we can get a value for the angle. In 3 dimensions, we have what are called direction cosines. And they are the direction cosines of certain angles. Alpha is the angle between the vector, so just the vector up to some point P. They're calling R here. Let's just call it V. So here's the vector V, and it's the angle the vector V makes with the x-axis, with the y-axis. Beta is with the y-axis, and gamma is with the z-axis. You can see that the cosines of these angles are the component divided by the magnitude divided by the length of the vector. So if you have the component and you have the magnitude, you can use the arc cosines to find alpha, beta, and gamma. On the other hand, if you have the alpha, beta, and gamma, and you know the length of the vector, you can find the components. Now we're going to take a look at vector subtraction. One way to look at vector subtraction is to see it's a combination of scalar multiplication and vector addition. So with the scalar multiplication, we say that minus b is just the same as b going in the opposite direction, and we add it to a. We know how to add the vectors together, so we would take b. Let me draw some vectors in here. I'll make them all be the same color for simplicity. So here's one vector. Let's say that's A. Here's B. Okay, now if I want negative B, it's going to be the same as B, but it's going in the opposite direction. There's B. Yeah, that's about it. Okay, it looks like slightly off kilter, but it doesn't matter that it's off base because we're going to move it around anyway. We're going to take this vector and we're going to move it up here and put it something like that. Okay, onto the vector A. Let's label these for right now. So here is A. Here's B. This is minus B. So moving around, it still maintains to be minus B. And then we connect these up. We have, needs a different color here. We would have, pick the tail of A to the tip of B. That would give us, to the tip of minus B, that's going to give us A minus B. Okay, that's one way to do it. It's not the handiest way, and it's not the best way. So let's look at a different approach. If we have B and we add to it the quantity A minus B, like here, of course, the B's are going to subtract out, and all we get is A. So this is a vector addition problem because this is a vector, and this is a vector. Previously, we had B plus A, for example, equals A plus B. So we knew B, we knew A, and we found A plus B. Here we're going to know B, we're going to know A, but we're going to find A minus B. So here's our A, here's our B, and we know that A minus B connects B to A, and there it is. So now that's vector subtraction in the coordinate-free sense. You don't have to reflect the B into the other direction. You don't have to move it around. In fact, you just leave A and B as they are and connect the two tips of them together. We will get a lot of mileage out of vector subtraction. In fact, in the second week of the semester, we're going to work with the vector equation for a line, and that's essentially using this vector subtraction. So let's see if we can understand it a little bit. We have here, remember how we got this. We said that B plus A minus B is equal to A. Now we can ask the question, what is the midpoint between B and A? Well, that means we would have B, and instead of going all the way to A, we only go halfway there. So that gives me an equation here, B plus half of A minus B. Work through that, and you get A plus B over 2, which seems very reasonable if you wanted the midpoint. But using this idea, you could get any point along this line. I'll do this, I'll write this equation again, plus alpha times A minus B. So if I use alpha to be 1/3, I would end up being 1/3 of the way down this line. If I have it 2/3, I've got over here to 2/3, 9/10, I'm going to be here. So I can vary alpha as much as I want, and every time I vary alpha and use this equation, I get another vector. And the vector points from the common tails here, tail B, up to the line. Let me use arrows, this look a little bit better. Okay. So I get all these different arrows along here. In fact, if I let it vary continuously, and I looked at the, try to get that all the way up there, if I looked at the points where these new arrows end, that would give me all the points on that line. A minus B is not the line between A and B. It's just a vector, and it happens to be sitting there, but it could be sitting anywhere in space. When we do this in the, like say, the next week of this class, we rename these vectors. I'll just put them here so we have a little heads up on them. We call this one R0, and we call this R1. We subtract those. Instead of calling it A minus B, we call it B. So the equation for the line becomes R0, just like we have a B here, plus some alpha times B. And it's customary to write this as B0 plus T times B. And as T varies, we trace out the line. When we go from 0 to 1, we'll start here at 0, because R0 plus T will just stay at R0. And when we go up to 1, we're all the way over here to R1. If we let T go beyond 0 and 1, in either direction, we can end up tracing out the entire line, remembering that in a line in mathematics goes from plus infinity to minus infinity. The line segment is the one that has the finite length. This subtraction idea, the subtraction of vectors, is used to solve many problems in geometry. And here is one of them. We'll go ahead and work through this. We have this, we're looking for the centroid of a triangle. Right? The centroid of a triangle turns out to be a place where all three of is a vector from the angle to the midpoint. All these medians intersect. And where they're going to intersect is going to be 2/3 of the way from the angle and 1/3 of the way down to the midpoint on the opposite line. We can do this without any coordinates, but we'll go ahead and put some coordinates to it. So we say that over here somewhere in space and time we have an IJK coordinate system with a K, an I, and a J with an origin. So the vector, the position vector coming out of this origin to A, I can write like this, because I'm going to say A has a coordinates of 4, 2, 0. So that's a position vector to A. It's also, it's kind of offset because this would have been down on the k-axis and be down the xy plane. Here's a position vector to B, and there's also a position vector going up here to C. Right. Now if I want the midpoint between A and B, just like we found out on the other page, it's just A plus B over 2. So it means I add the two components of A and B together, component by component, and divide by 2, and I'll get 5/2 I plus 5/2 of J, and of course 0 in the K. The numbers here aren't that important. It's the procedure. So by using this procedure right here, I'm able to find the midpoint of the line AB down here in the triangle. Now if I want the line from C down to M, I can give that as M minus C. So now there's a vector here. Whoops. There's a vector here. I didn't switch tools here. Yeah. Okay. A vector to M. So that's what's given here. That's the coordinates of the endpoint of the position vector to M. Now if I want the line segment here from C to M, I would subtract M from C, which will give me something. Let me figure it out here. Okay, so I've had 5/2 minus 1. That's going to be 3/2 I. So 5/2 minus 1 again, so that would be 3/2 J. And I have 0 in the K here and 3 here, so that's minus 3K. Okay. That is the vector from M to C, and that's some coordinates of it, but it is not, okay. It would not give me the coordinates of that centroid. To get to the coordinates of that centroid, I have to add C and then travel. So I'm going to go up C like this, and I'm going to travel 2/3 of the way back down, and then I'll hit the centroid. And if I want its coordinates, then I'm getting the coordinates from the position vector pointing to it. So that would be C plus 2/3 CM. So I have, that would be 1I plus 1J plus 3K for C. And now I'm going to add 2/3 of this number, so that's 2/3 times 3/2, so I get 1I, and then 2/3 times 3/2 for the J, so I get 1J, and now it's like a -2 in the K direction. Okay, I can add these together, and I'll put it in pointed brackets, 2, and then get another 2, and then I got 3 minus 2, which is 1, and those are the coordinates of the centroid of that triangle. Again, the numbers are not important. What's important is to remember what you're dealing with, whether you're dealing with just a vector or position vector. What do the coordinates really mean? There's several other problems that are also solved this way, but that is a use of the subtraction of vectors.